Okay, so one of the forces that we obviously want to come back and calculate the work done by is the gravitational force. And so if you have an object that's moving around in the Earth's gravitational field, well, near the surface of the Earth, we know the gravitational force is constant, so we can calculate the work done by that force as just being the force dotted in with some displacement. So if you have some object sitting in the Earth's gravitational field, the gravitational force is pulling it down. If it moves down, then the force and displacement point in the same direction, and the work done by the gravitational force is positive. If, on the other hand, you move an object upward, so here's a situation where the displacement points up, the gravitational force points down, they point in opposite directions, and the work done by the gravitational force is negative. So conceptually, that dot product is telling us that it's fairly simple to figure out what the sign of the work done by the gravitational force is going to be, depending on whether your object simply moves up or down. Now, I can break the gravitational force up, and again, in a two-dimensional way, I'll break it up into an x component. There's no horizontal component for the gravitational force. It points downward. So here's an mg. So notice I've clearly picked up to be the positive direction here. And if I move my object, well, then I've got some displacement that I can also break up into the x component I hat plus the y component j hat. So for my displacement, this is just the change in x, and the y component is just the change in y. So when I do the dot product between these two, well, I'm going to get x components multiplied together. That's going to give me 0. Y components multiplied together plus z components multiplied together. So I end up with an expression that's just negative mg delta y, where delta y is my vertical displacement. And as a displacement, we do have to take into consideration which direction we pick to be the positive direction. So it is built into this equation that as the object moves up, that has a positive vertical displacement. An object moving down has a negative vertical displacement. So we know that the work done by an object moving down, done by the gravitational force on an object moving down, that needs to be positive. And so something's got to cancel out this negative sign. And sure enough, if my vertical displacement is negative when my object moves down, then this negative will cancel out that negative, and I'll be left with a positive value. For objects moving up, I know that the work being done is negative, and so my vertical displacement being positive for objects that move up gives me a work that is negative. So it is very important that you remember, if you choose to calculate the work done by gravity this way, that it's built in to what we define delta y to be, which is the positive direction. To sort of get around that, the way that I'll tend to deal with the work done by gravity is to say, well, it's pretty easy to figure out whether an object is moving up or down, so I can take care of the signs right up front. And then all I want to do is just multiply together 3 positively valued scalars. So positive mass, positive 9.8 meters per second squared, and then delta h is just defined to be the vertical distance moved. So this should be delta h, not delta y here. But that positive distance, and so multiply these 3 things together, I'm going to get a positive number, and then I'm going to take care of the sign. So obviously I will let the sign be positive when my object moves down. We'll let the sign be negative when my object moves up. So this is the way that I'll tend to deal with calculating the work done by the gravitational force, because A, it's easy, and B, I make sure that I get the right sign, because I'm just going to be responsible for making sure the right sign gets placed into my equation depending on whether my object is moving up or down.